All right, next thing we want to talk about are capacitors in series. Series capacitors. Now, if you remember from last year, series means that you're going to have one item lined up one right after the other in one nice straight line. There won't be any branching points in there. And I am going to refer back a little bit to series resistances that we had a while ago. Now, let's call this guy C1, C2, and C3. That's pretty straightforward. Now, this is going to be positive. This is going to be negative. Conventional current's going to go this way. Electron charge flow is going that way. It's electron charge, and there's our conventional current. All right, so turn this on. It's going to start to build up a charge across the capacitors. Now, let's think about something here. Remember, there's an air gap in here. This guy is going to create a positive charge on this side. And of course, you're going to get a negative charge on the opposite side. The positives are, of course, going to draw electrons over to this side of the plate. And of course, on this side, it's going to become positive there, negative here, positive here, negative there, going right across. Now, if I look at these sections in between the two capacitors, like this little block right in there, looks like an H. This is totally disconnected from the other side. There's no way charge could flow across these plates unless you get dielectric breakdown, unless there's actually a spark that fires across, which means for that whole section, Q is going to be 0 for this whole little H section there. If that's true, that means one side's going to have negative Q on it. The other side's going to have positive Q on it. Now, capacitors have equal and opposite charges on both sides, which means I'm going to get positive Q on this side, negative Q there. This next capacitor is going to have exactly the same charge on it. And the following capacitor after that is going to have the same charge on it. So in series capacitances, whatever the charge for the system is going to be is going to be equal to the charge. Whoops, sorry. Wrong thing there. Let's get rid of that. Yeah, no. Charge for the system is going to be equal to the charge on 1 plus equals the charge on 2. And that's going to equal the charge on 3. They're all going to be equal to each other. All right. This is similar to series resistances. I know we haven't covered an AP yet, but we did them last year, where we know that the current total, the current of the system, is going to be equal to the current across 1 equals the current across 2, which equals the current across 3. That all makes sense. Now, let's talk about electrical potential, V. Since we know that V is going to act like electrical pressure, anytime we've got something that's in series, that electrical pressure can't all be lost across a single device. It can't be lost all across the first one, or the second one, or the third one. It gets shared across each of these guys. So whatever the voltage is that I drop across one, plus the voltage drop across the next one, plus the voltage drop across the third, are all going to add up to the total voltage being applied to the circuit. And this is, of course, just like resistors. Exactly like resistors. Now we know this. C equals Q over V, or V is going to be equal to Q over C. So let's put this all in here. Q total over C total equals Q1 over C1 plus Q2 over C2 plus Q3 over C3. And since these Q's are all the same, we can drop them all out and we're left with 1 over the total capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Okay, let's do a quick example. We've got a series capacitance circuit with two capacitors going across. C1 will allow to be 10 farads, C2 be 15 farads. Those are crazy amounts of capacitance, but I'm not all that worried about it. What we want to do is we want to analyze the circuit. We want to find out what's going to be the charge across each one of these capacitors and what's going to be the potential across each one of those capacitors. To do this, let's set up a little chart. C, Q, and V. Now I'm going to call this guy 1, 2, and T for total. Nice and easy. And we're going to write in everything I know. I know C1 is going to be 10 farads, C2 is 15 farads, and my total here is going to be 120 volts. All right. Now, in order to solve this, I want to reduce this. I want to find an equivalent or total capacitance for that entire circuit. In order to do that, well, we're going to have to solve for C total. And that's not all that difficult because in a series circuit, 1 over C total is going to be equal to 1 over C1 plus 1 over C2. That's 1 over C total is going to equal to 1 over 10 farads plus 1 over 15 farads. That means 1 over C total is going to be equal to 0.1 plus 0.0667, which is going to be 0.1667. We take the reciprocal of that, and C total turns out to be 6 farads. I'm going to fill that right in here under my total, 6 farads. All right. Now that that's solved, I can find out what the total charge in the circuit is. My total capacitance, I'll write up here, 6 farads. I still have 120 volts. That's my potential across the circuit. Now let's solve this. For the total, C equals Q over V, but I'm going to put little t's next to it so I know I'm dealing with the entire circuit here. I've got a total capacitance of 6 farads. Q total I want to find. V total is 120 volts. Okay, so anyway, we know the total capacitance. We know the charge. We are looking for the charge, excuse me. We've got the total voltage. Let's put that potential in there, cross multiply. You get 720 coulombs. Now we always want to ask ourselves what is going to be the same. And in the series circuit, let's make that a little neater for you. Did goof a little earlier. We know that Q total is going to be equal to Q1 is going to be equal to Q2. It's all 720 coulombs. Now, since that's the same, it's pretty easy to figure out what the voltage is going to be. Across C1, since we know the charge is going to be the same in each one of these, 720 coulombs. Crazy, but we'll use an example. That means V1 is going to turn out to be 72 volts. Do the same thing for C2, Q2 over V2. We're going to have a 15 farad capacitor. We happen to know that there's 720 coulombs over those, divided by V2. And so that's going to turn out to be 48 volts. So let's put them up here. I'm going to get 72 volts across this guy. And I'm going to get 48 volts across this guy. And as we notice, this all works out because in the series circuit, V1 plus V2 has to equal V total, and it does. And we're cool with that.